Patel in 1994 with a vision to, and with the various business structures like solar, wind, fabrication, and galvanization. Here, I'll like to tell you that currently we are commissioning India's largest galvanizing bath of 14 meter by 3.8 by 3 meters. So about KP, these are there are 28 companies in total, and these four groups are majorly there. Mr. Moinul Kadwa is the director, whole-time director for our this KP Green Engineering sector. So we'll talk about the steel, the future of steel and the growth of steel in coming years. India and Southeast Asia are emerging as a separate engineering growth, with India especially poised to nearly double its steel demand in 2035. Global steel demands is projected to be rise modestly for approximately 1,150 million metric tons in 2024 to between 1,850 to 1,900 million metric tons by 2035, with most growth concentrated in India and Southeast Asia. China's apparent finished steel demand is projected to decrease from between 900 to 950 million metric ton in 2024 to between 800 to 850 metric ton by 2035, driven by structural shadows in China's real estate and construction sectors. So the future of steel construction in India is poised for rapid, sustainable growth, driven by a projected 6% CAGR in demand and target of 300 million tons of productivity capacity by 2030-31. Sorry. Key trends include escalation, urbanization, massive infrastructure development, a shift towards green steel and pre-engineered buildings. India is the second largest steel producer globally. Construction sector contributes 8 to 9% to GDP. Infrastructure-led growth, transport, energy, urbanization. Shift from RCC dominant construction to steel construction. Steel intensity still lower than the developed country, developed economic. So you can see the sector-wise demand and in each sector. Key trends in Indian steel industry: the massive demand growth driven by infrastructure construction and real estate. Indian steel demand is expected to reach 240 to 260 million ton by 2035. Infrastructure focus: the government focus on building road, bridges and railway is boosting structural steel demand. Green initiatives: the industry is moving towards decarbonization using electrical arc furnaces, green hydrogen and steel slag for infrastructure to meet sustainability goals. Pre-engineered buildings increase adoption for PEB, enhancing the speed, quality and durability in the construction. The market growth: the structural steel fabrication market is expected to reach USD 30.27 billion by 2030, growing at the rate of 6.38 CAGR. Capital expansion and policy push. Capacity expansion by steel manufacturers like Tata Steel, JSW, Steel Authority of India Limited, ArcelorMittal, Nippon Steel India, National Infrastructure Pipeline, PM Gati Shakti Master Plan, Industrial Corridor and Logistics Parks, renewable energy structures, solar, wind, steel demand, growing FDI and private capex in manufacturing. There are certain challenges like economic risks, raw material price volatility, iron ore, coking coal, high logistics and energy costs, high carbon intensity of steel production, ESG compliance of pressure, global carbon border taxes, it's a further risk, low steel penetration in residential housings, competition from reinforced concrete, and technology gaps in advanced fabrication. The shift towards green and smart steel, scrap recycling and circular economy, low carbon green steel initiatives, automation and AI in manufacturing, beam integrated steel construction, pre-engineered buildings growth. The future competitive advantage is low cost plus low carbon with high efficiency. The road towards 2025 to 2035, rising infrastructure investment, sustained demand, increased steel usage in urban high risk and modular constructions, export competitiveness in value-added steel, digital supply chain integration, policy support for green steel construction. Executive Council steel construction will be core enable for India's infrastructure, manufacturing, and 5 trillion economy ambition. Long-term outlook structurally positive, but sustainable transition is critical. So I'll talk about the current factory which we have, where we are producing this structural steel poles and galvanizing structure. It is a 55 acres of land with 400 to 500 metric ton per annum capacity. Asia's largest kettle, 90,000 MTA per annum. BSc listed company, group excellence, 31 years. And in Dabasa, we have 20,000 square feet. Production capacity, 53,000 metric ton per annum. BSc listed company and group excellence of 31 years. So these are the products and clients, tower structure, transmission line towers, wind lattice towers, telecom towers, sustainable and switch from structures, high mast towers, and monopole towers. Solar building and trays, MMS solar modular structures, solar trackers, pre-engineered buildings, cable trays, perforated cable tray, ladder type cable tray. Then we are into crash barriers, which we have recently tested and it has been passed for international standards, electrical isolators, double bed isolators, galvanized earthing strips. We have a capacity of 10,000 tons per month galvanizing capacity. Anybody having requirement of that, you are always welcome. So we bring our 31 years of construction expertise to the industry, offering PEB and heavy fabrication solutions. Our commitment towards innovation perception is efficiency setup part. So decades we have in-house design also. Largest galvanizing facility, quality excellence, timely delivery, and massive infrastructure. We are expanding with another 100 acres of land with 2 more factories to be commissioned by next year end. These are the certain certification and awards which we have been given. So these are the sectors served. Thank you.
Thank you, Mr. Reina, for sharing your expertise. We now move to a significant infrastructure showcase. Please join me in warmly welcoming Mr. Satish Lal Suneja, Deputy Director, along with Mr. Krishna Prabhu, Senior Manager at Nippon Koi India, for a joint presentation on Chennai Metro Rail Project Phase 2. This transformative urban mobility project represents scale, complexity, and engineering precision. We look forward to understanding the design challenges, structural solutions, and execution strategies behind this landmark development. I welcome you with a big round of applause, ladies and gentlemen.
First of all, thank you to SSMB for inviting us to do this presentation, and welcome all. So I will be putting up a brief outlook of what Chennai Metro Phase 2 is bringing to this city and a nation altogether, as well as we will discuss what is or how the steel is used, or what is the, what are the problems we faced. We will take one case study, not exactly with CMRL Phase 2, but a problem which are going to come in future in many cities, because a lot of tunneling is happening, and urban tunnels are all around below the roads, and then you have to plan a flyover. So we will discuss about that, something which we are doing right now. Okay, next one. Okay, so I will be discussing about project, usage of structural steel in elevated, underground, and tunneling, And then we'll go for innovative use of structural steel in two cases here. So first about the project. If we see on the left side, this is the map of phase 2, which is coming for Chennai Metro. The violet portion is one which is all elevated, and the green portion is all underground. And if we really see, it is one of the biggest project being executed at one point of time in a city. 116 kilometers, out of which 41 kilometers with about 41 stations are underground. A massive, massive project. No one has taken 40 kilometers of underground, at least in India, at one go. Delhi has done about 300 kilometers, but they have been doing in last 5 stages or 5 phases. And out of this 300, underground is not to that extent. Okay. So what typical underground station look like? So a station underground will be having generally 2 levels, one for concourse and one for platform. That is a typical station. So here you see all these typical station. However, this project, at least Chennai Metro Phase 2, have various stations. So normally the depth of underground station is around 20-22 meters. But this is a project where we will have few stations going up to 40 meters deep and having 4 levels of decks with 2 levels of tunnel passing over each other. There'll be few stations where not entire 2 tunnels or 2 platform can go together, so they'll be stacked up because of land constraint. A typical elevated station is again a 2-level station. This is a typical station in Chennai Metro. Most of the station will be this. One thing which you might have realized here, that whole of the station is supported on one single central pillar. Earlier designs, either in Chennai or anywhere else, were used to be that both sides you had pillars. So now it has evolved, design has evolved to the stage where only single pillar is being there. And a lot of precast elements are being used. The thing is, here there are few stations going up to 34 meters. Normal height of a station of rail level is around 12 meters, 13 meters. But there are stations which are going up to 34 meters in Chennai. Okay, there will be 4 stations in Chennai will be double-decker, which are in construction. Again, a new evolvement in last few years, which has happened. And Chennai is leading now with almost like 5-kilometer section is double-decker. A typical depot where trains will be serviced, train will be stabilized, and the workshops and others. This is a Madhvaram depot, which will happen here. So underground methods which we have adopted is, generally speaking, for stations, we have adopted cut and cover tunnel method with diaphragm wall on both sides. One, again, first of the thing which has never happened earlier, that in this project, in this city, right now 23 trench cutters were working, which has never happened. Earlier or any other city, the stations were being built by diaphragm wall, but with grabs, which was much easier. Chennai is doing with the trench cutters, and that too 23. Typical method adopted for tunneling in general in industry is either NATM, TBM, or cut and cover. Here in this project, since about 40 kilometers is underground, so a lot of TBM tunneling has been adopted. So 19 TBM are in Chennai working, which has never happened in India. The world record was 21 TBMs in Doha at one point of time. Here in Chennai, 19 TBMs are working. the general method for TBM, as we said, in TBM also there could have been earth pressure balance machine and slurry machines. In Chennai, all TBMs are being done with earth pressure balance machine. Earth pressure balance machine principle in general is that, you see the red portion, that is the bulkhead. When you excavate, that soil comes into this, it balances the force which is being exerted at that level, and the white portion you see, that remains in atmospheric condition. So the pressure in bulkhead could be 3 to 4 bar, nobody can go there. And that once that pressure is being released through that screw conveyor which is going red slant portion, and excavation muck is coming out. Now, Netum is used only for cross passages. Cross passages is a feature in underground tunneling. Since both parallel tunnels are going for fire reasons, every 250 meters you have to connect these two tunnels. And this is one of the most complicated and one of the risky operation which is being done always in construction of underground. Now, I'll just skip because I have limited time. Usage of structural steel, since this forum is for structural steel. So normally in structural steel, what we have used is pre-engineered building, which will look like this. Will you imagine the scale of this project, that overall, although it looks like one station is only how much, maybe 150 meters by 20 meters, but altogether, there is about 250,000 square meter of pre-engineered building which are going to happen here. 250,000 is just a rough estimate, maybe even higher. If you add depots, there are 2 depots and other things. Structural steel is not that much in underground construction if you really see. However, for doing underground construction or even in elevated with most mechanized construction nowadays, it is being used for enabling works. All excavation in underground structures are mostly supported by struts and wailers, which are very, very heavy sections. If you don't do diaphragm wall, you go with bottom up, then you have soldier piles, H-beams are being inserted there as piles for lateral restrainment. And for elevated, launching girders are being used. Launching entries are being used. Now, for tunneling, you see there are heavy reaction frames. There are supporting utilities, conveyor belt supports. Somewhere in longer tunnel section, you have to take out muck through conveyor belts. All these are being done with engineered structural steel. Now, I'll go into innovative use of structural steel in underground metro. I take 2 examples. One is, this is a case around Commonwealth Games time. October 2010, or September 2010 was supposed to be Commonwealth Game. In Delhi, there was a line which was connecting existing Central Secretariat to Gurgaon. And one of the stations, they could not get land in between, Chhatarpur. And land was obtained only to the, I think, October 2009. So there was only about 10 months which were remaining. What good thing they did, they planned this station with structural steel. So they precasted, prefabricated whole of the structural steel in the factory, took it there, and in 9 months flat, they made this construction. In general, on elevated station, it takes almost like 30 months as a minimum on a 2-level non-complicated station. And this was done in 9 months. So I used to say, wherever RCC fails, steel comes into picture for saving. Even if it is not the main component, but it saves many times. I will skip this one. The second thing which we are going to present, I'll ask Krishna to give 10 minutes. We have a case here where we have, basically speaking, a tunnel, elevated corridor from at St. Mount Road of 4 kilometers. And the problem is that it is coming exactly over 2 tunnels which are below. So now we have a problem because if we do piling, it may hit the tunnels. So we had 2 solutions to find out of which we chose one, and why and what is the advantage. I'll ask Krishna, he's the designer for this one. So I'll just ask him to present this one. Yeah, thank you.
Thank you. Thank you, SSMB, for this opportunity. See, this project has been divided into 3 parts. First one is non-tunnel portion, where we have adopted the pile foundation. Second one is tunnel portion, where we adopted the open foundation. And one more portion is metro station. We do have 2 stations. One is Nandanam and Tenampet. So this project is starting from Tenampet to Saidapet. And we do have 2 approaches also. That is coming around 127 meters. Basically, this proposal has been started in 2010 when we started the first underground metro in Chennai. So that time, Highways has given the proposal that upcoming project is going to come from Tenampet to Saidapet. It's a 4-lane project. So they have given the loads. So based on that, the tunnels are designed. And there is a limitation also. They have given that 60 kPa, whatever foundation loads which is to be designed for the elevated corridor. So we have to restrict the tunnels for the 60 kPa. And the tunnels are like 6-meter diameter and 275 mm thickness, and we do have 7 cross passages also. So, and the tunnel depth is from the ground level to the top of the tunnel is 10 meter to 14 meters. So why we have gone for the steel bridge? Basically, we have 2 underground metro station and then tunnel. And another problem also we had, the geological profile. Basically, you might have seen before 5 years, there was one bus was stuck in the ground and we had some path hole. So the soil is not properly good. So based on that, we want to reduce the load. So we have gone with the alternative option called steel bridge. There is a existing metro station and we do have a dimension of 235 meters each station. And these station walls are designed for the proposed flyover. Initially, it's like all the plunge columns are designed for the future flyover, and these stations were completed in 2008. The main advantage of this steel bridge is faster construction, and we can go up to longer spans, and better performance in the dynamic loads, higher strength ratios, and ease of maintenance and modification. So this is a basic soil profile. We have the SBC of 8 to 14 ton per meter square. So the loads, whatever we are giving in the bridge, it has to be reduced. So for that, we have designed it actually, sorry. When we are going for the foundation, we have 132 numbers. Non-tunnel portion, we have 22 numbers, and then metro portion, we have 69, and in station portion, 41 numbers are there. So this is a typical section, what we have adopted above the tunnels. And we have adopted the methodology called, we have improved the ground by means of micropiling and then geotextile layer above the tunnels to reduce the load. And we have made the analysis also through Plaxis, and then we got the stresses well within the limit. This is a typical section for the non-tunnel portion, which is having the pile foundation. And we have adopted the portals over the stations. We have adopted the pier design as a hollow section, and we have adopted the thickness from 32 mm to 50 mm. And the welding thicknesses are like 8 to 12 mm. And in between the base plate and then the pedestal, we have adopted the GP2 grout. This is the typical pier cap for the, This is the typical pier cap section, what we have adopted for the piers, whatever we have adopted in the this one. And we have a spans varies from 20 to 37 meters. And we have adopted with 1.65 meter depth of girders and 5 girders arrangement for the 4 lane. And some of the side photographs for you. And this is the pier cap adapter we are using for the temporary structure arrangement. Once we have loaded the superstructure, so we need to support the girders. For that, we have prepared this temporary arrangement. Once the superstructure is made as a composite, complete, and then we will remove this adapters. And progress of this steel girder erections, now it is going on actually. Thank you.
I'll just add one thing into this, that, the thing that the load on this tunnel has to be 60 kPa. We have installed all instruments which are required, and we are monitoring this, which will we keep on monitoring after even the fully it is loaded, 1 year after that. So until now, there is absolutely, even when the heavily loaded trucks are on this section, including the dead load, it's not even 10% of what 60 kPa is coming into the tunnel. Okay, any question if at all, because I just tried to complete this in 30 minutes, which was given to me. That column, yeah. This one. Yeah.
This one.
No, that pier section. Yeah, 32. Yeah, this one.
This one. This has been done with welding, sir, actually. It's a plate, actually, 32 mm plate. 4 plates are connected by welding. It's a fabricated structure.
You know, when we were just outside, we thought APL Apollo section would have been best if it was available, yes. Road section, yeah.
No, sir. Actually, here we are using the butt joint. What we are doing is, we are doing the welding over here, and also we are doing the welding here. It's like 4 corners we are doing the welding, and inside also we are doing the welding.
You can't develop that sort of a strength, no? If you see just right corner, you are showing a welding there. Your section is inside, no? So 32 millimeter, you are having some 10 mm
yes, sir.
on this.
It will connect it. After that, we have some space to do the welding.
Correct.
Yes.
So in that 10 mm, you are going for the fillet weld.
Fillet weld. And then inside also we are doing the welding.
But how you can go inside?
No, sir. It is prefabricated only, no, sir. Initially, what the fabricator is doing is, they will make 3 plates.
But you will get 3 side you can weld it, not on all 4.
Inside it is 1.2 meter, no, sir. Size of the, yeah, inside they will go and then they will do the welding. And we have the stiffness also inside, up to 1.2 meters. When we have the vehicle collision or any lateral loads are coming, to arrest that, we have a stiffness.
You are right. And they are giving you 1200 section, I think.
Yes. No, sir. Sir, only deck slab is composite, sir, actually. No,
Deck
sir.
slab is composite.
It is only steel structure, sir. It is hollow steel column. And our pier caps also like, it is also fully a steel. It is, yes. Yes, sir. Sorry, sir?
Just,
32 mm welding,
Yes, sir.
you need thermal treatment.
thermal.
Thermal. Yes, sir.
Yes. Yeah.
Yes,
Has it been done? Has it been done?
Yes, sir, it has been done, sir.
So I have questions. Pier, how it is supported in the base?
Here,
In the base, in the ground?
in the base.
Ah.
We do have a base plate. The PSR, the loads will come to the base plate. It has been connected through the bolts. You can see here.
So it means there is no filling of concrete inside the...
No. It's a hollow section. We have a stiffener plates here. Inside the column, we have a stiffener plates,
Okay.
which is connecting like a cross. And we have a stiffener plates outside also. And we have a bolted connections.
What about the protection, corrosion protection, anything
We'll
inside?
do the pier protection wall. After this, we'll do the pier protection wall.
No, inside of the column, because it's a hollow, it is not concrete field.
Anyway, it is 32 mm, right? What corrosion will happen? Because we understand that if it is 20 mm or less than 20 mm, there may be a corrosion. It is 32 mm, so there won't be any corrosion. So we have not given any, because it is fully closed.
Okay. There will not be any venting of air or there will not be venting.
Anyway, we are doing some coating also inside.
Okay.
We will do it actually. We are doing it actually.
Okay, thank you.
Okay, thank you.